Okay, let's talk about maybe the single biggest, most expensive vulnerability in our entire energy system.
I think I know where you're going with this.
Buildings. Globally, they consume something like 40% of all the energy we generate, a huge slice of the pie.
And if you're looking for the main culprit in all that energy use, you find it pretty fast. It's the windows.
Right, they might only be, what, 8% of a building's surface? Maybe 30% if you're in a glass skyscraper?
And yet, they're responsible for almost half of the heat that escapes. It's a massive thermal leak.
Half. It's wild. So today, we are diving deep into some research that might just plug that leak for good. Welcome to the deep dive.
Our mission is to unpack a material that is, get this, completely transparent, but it insulates better than a wall.
We're talking about turning glass from a liability into an energy fortress. The material is called MOCII.
That's MOCHI for Mesoporous Optically Clear Heat Insulators.
And we're pulling our insights directly from the source, a paper called Mesoporous Optically Clear Heat Insulators for Sustainable Building Envelopes, which was published in the journal Science.
It's a really fantastic piece of work from a team at the University of Colorado Boulder. It was led by corresponding author Ivan the Smolyuk, along with Amit Bhardwaj, Blaise Fleury, Bohdan Senyuk, and many others.
So our goal today is to figure out the alchemy here. How did they achieve near-perfect invisibility and super insulation in one material?
And more importantly, can they actually scale it?
Okay, so let's start with the problem they had to solve first. The holy grail for decades has been a truly clear aerogel.
Right. Everyone knows that aerogels are incredible insulators. People call them frozen smoke.
But you can't put them in a window
Yeah.
because they're hazy. They always look like you've trapped fog in a piece of glass.
And that haze has always been the deal breaker. It all comes down to the internal structure.
It's cores, right?
Exactly. Old school aerogels have what are called polydisperse pores. They're all different sizes, totally random. Some are tiny, some are huge.
And when light hits that kind of random, messy landscape,
It scatters. It just bounces off in every direction, which is why the image you see through it is blurry or milky. They just fail the very stringent optical requirements you need for a window.
but MOCHI cracked that code.
Mm-hmm.
And they did it by creating what the authors call a pre-engineered metamaterial.
That's the key phrase. This is not some random foam. The MOCHIs are built from these tiny polysiloxane tubes that form a perfect graph-like network.
A geometric network.
Yes, and the key is the precision. Every single structural feature is controlled to be under 50 nanometers.
50 nanometers. Okay, just for scale, a human hair is about 80,000 nanometers thick. So this is just an impossibly small, delicate structure.
And that nanoscale precision is what leads to the thermal breakthrough. This is where the physics really flips on its head.
Okay, lay the numbers on us.
The thermal conductivity of these MOCHIs is incredibly low. We're talking 10 to 12 milliwatts per Kelvin meter.
That sounds very technical. Can you translate that for us? What does that mean in the real world?
It means it insulates better than the air it contains.
Wait, what?
Think about it. Still air is the insulator in a normal double-pane window, and its thermal conductivity is around 27.
So MOCHI at 10 to 12 is more than twice as good.
More than twice as good.
How is that even possible? How can you put a structure inside a pocket of air and have it insulate better than just the air itself? That kind of breaks my brain.
It's just brilliant design. It's all about molecular choreography. See, air molecules transfer heat when they get warm and then collide with each other.
Okay.
The average distance an air molecule travels before it hits another one is called its mean free path. And that distance is about 60 to 70 nanometers.
60 to 70. Got it.
So the researchers deliberately designed the pores in the MOCHI to be smaller than that, much smaller.
Ah, so the air molecules can't travel far enough to bump into each other?
Exactly. They end up colliding with the cold, rigid pore walls more often than they collide with each other.
So you've essentially shut down the main way heat moves through a gas. It's like you've put the air molecules into millions of tiny individual thermal quarantine rooms.
That's a perfect analogy. You're strongly inhibiting that gas conduction. And on top of that, the solid network itself is a terrible conductor of heat.
So heat just hits a dead end everywhere it turns.
Pretty much. And the amazing thing is, by solving the optical problem, by making the pores tiny and uniform to stop light scatter, they also solved the insulation problem.
And the optical properties they're just as remarkable.
Oh, absolutely.
So it gets rid of the haze. But it's not just not hazy. The data shows it transmits more than 99% of visible light.
Which is actually better than a standard pane of glass. Glass is usually around 92%.
So it's literally clearer than glass.
And that comes from another nanoscale trick. It's all about reflection.
Let's talk about that. Why does glass reflect light, that glare you see?
It's because of a mismatch in the refractive index between the glass and the air. Basically, light bends when it crosses that boundary, and some of it just bounces right off.
Okay.
But the MOCHI material is mostly air, so its refractive index, around 1.025, is incredibly close to the refractive index of air itself, which is about 1.0003.
They're almost a perfect match.
So when light hits the MOCHI, it barely even notices it's there. It just passes right through.
That's the Star Trek cloaking device effect.
Oh, yeah.
I mean, the paper says the total reflection is only about 0.02% compared to like 8% for normal glass. You lose nothing.
And this creates a huge advantage for manufacturing. You compress two slabs together, and they form what's called an optical contact. They merge seamlessly.
Which solves the scaling problem.
It helps.
Because that's where these miracle materials usually die, right?
Yeah.
You can make a tiny piece in a lab, but you can't make a window out of it.
Right. And they tackled that head on. They use a solution-based process. It's basically self-assembly. They put these surfactant molecules in a solution, and those molecules naturally form the scaffolding for the structure.
Nature does the hard work.
Exactly. Then they fill that template with the polysiloxane gel. The really tricky part is getting the liquid out without the whole thing collapsing.
That's the supercritical drying process, right? Using CO2 at really high pressures.
That's the one. It's complex, but the team, including researchers like Aldo Abraham and Vladislav Čerpak, they successfully scaled it up to square meter dimensions.
Square meters. Okay, now we're talking. That's a real window.
That is absolutely a building-relevant scale.
But if it's mostly air, you have to wonder about durability. What happens when it rains or gets dusty?
They tested that extensively. First off, polysiloxane is already used in construction sealants, so it's a known, robust material.
Smart.
Second, it's fire retardant, which is critical for building codes, and it's super hydrophobic. Water just beads up and rolls right off.
And the long-term tests.
The tests showed the performance held up even after simulated exposure to about 5 years of things like acid rain and dust. It's a surprisingly durable nanosponge.
So let's put it all together. You take this durable invisible material and you put it in a window unit, MOCHI-IGU. What's the real-world performance?
This is the number that will make architects sit up and listen. The R value. A 2.5 centimeter slab, which is about an inch.
Yeah.
It achieves an R value of about 15.
R15. Okay, for everyone listening, a standard double-pane window might be R3, maybe R4 on a good day. A well-insulated wall in a modern house is R13 to R19.
Exactly. So you're talking about a window unit with the same thickness as what you have now that insulates better than most of your walls.
That completely changes the game for building design.
It really does. The simulations they ran showed that you could increase the window area of a building to 30% and still massively reduce the overall energy waste.
Then there are other benefits too, right? Like soundproofing.
Oh, yeah. A huge one. The MOCHI units were 5 to 10 decibels better at blocking sound than conventional windows. Quieter homes, quieter offices.
Lower energy bills, perfect clarity, and less noise. It's already a win. But the last application in the paper, that's where it goes from saving energy to actually generating it.
The autonomous power plant. This is where it gets really exciting.
So what did they do?
They took a black body solar absorber, basically just a black plate that soaks up heat, and they encased it in MOCI.
Okay, so the MOCHI, being transparent, lets all the sunlight in to hit the black plate.
Right, but once that sunlight turns into heat, that heat tries to escape as infrared radiation.
And the MOCHI's nanostructure is a brick wall for that kind of thermal radiation.
It's the ultimate greenhouse effect. It traps almost all of the heat, and the results were just staggering. They got stagnation temperatures on that absorber of around 300 degrees Celsius.
300 Celsius. That's 572 Fahrenheit.
From unconcentrated sunlight.
Wow. That is more than enough to run high-efficiency hot water systems, heating, even run certain types of air conditioners.
The authors point out that parts of your building could become their own power plants, not just saving energy, but actively generating it. Enough to make a single-family home energy neutral.
This really moves us past thinking of buildings as, you know, a collection of separate parts, solid walls here, leaky windows there.
The entire building envelope becomes a single, high-performance, energy-smart skin.
So to wrap this all up, let's do the key takeaways. First, this is a true insulation revolution.
Right. MOCIs have a thermal conductivity lower than still air itself, all because those nanoscale pores physically stop heat transfer.
Second, they achieve true clarity. It's optically better than glass over 99% light transmission, almost zero reflection.
And third, this pushes us toward energy autonomy. You can use this material to turn a building's skin from an energy liability into an energy-generating asset.
It's like taking the technology from the Mars rover's aerogel insulation and making it practical for your living room window.
Precise.
Okay, so if a material can make windows as insulating as a wall, block out the noise from the street, and turn sunlight into 300-degree power. Here's the thought I want to leave you with. How long until every structure we build, from a skyscraper to a greenhouse, is designed from the ground up to be its own self-sustaining power plant?
Thanks for joining us for this deep dive into what could be the future of how we build.
If you enjoyed this breakdown, be sure to subscribe to The Deep Dive for more curated knowledge. We'll see you next time.